Hello.
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 Hello. Can you hear me?
Yeah, I can hear you. Hi. How are you? Okay, let's start. Okay. We completed till satellite, right? Non-linearity. We were dealing in the non-linearity, right?
Yeah.
Hello.
Yeah.
Yeah, basic part of non-linearity we did. Memorialists we did.
Yeah.
I think we have to start from 1 dB compression point, right?
Mm-hmm.
Yeah, 1 dB compression point. Okay. So basically what happens in our non-linear system, we do not get power output as a linear with our input power. Okay. Power output are basic in non-linear system. Due to non-linearity, the power output is not directly proportional to the power input. Okay. So what happens due to the non-linearity, we have the different other components apart from the input power. Okay. And that changes our or that makes the power to drop when we increase the power. So actual what happens, suppose this is your power output and this is your power input. Okay. So you are giving power input as a input power as a cos omega t. 1 minute. Suppose you are giving your power as a cos omega t, but due to the non-linearity, you might be getting different components of power, different components at output. Okay. Suppose you have given this one, but due to suppose this is your non-linear system. Okay. Suppose this is your non-linear system. Understand it, and you are getting yt when you are sending xt. Okay. And this is your non-linear system. And due to the non-linearity, your yt will be have different component a1 xt plus a2 x square t plus a3 x cube t. Okay, because this is non-linear. Okay, so you will be getting your output in the non-linear function. So apart from your power input, suppose power input, you will give different other terms. Okay, so here what is your it is a cos omega t, it is a2 a square cos square omega t, and apart from that it is a3 a cube cos cube omega t. Okay. So if you do its calculation, you will get different components. One a2 a square 2. This is your DC component. Okay. Apart from that, you will be getting some other component a1 plus 3 a cube plus 4 cos omega t plus a2 a square by 4 cos 2 omega t plus A3. You are getting your different frequency, but you can see which frequency you are targeting, cos omega t, right? This is your cos omega, but here you see apart from you are getting this much of gain, you will see that your gain get compressed. Your gain get compressed when you are passing it to a non-linear system. Okay, so what happens? We have a 1 dB compression point. Suppose this is your P input and this is your P output. So what happens? Suppose this is your actual gain is like that, but you were expecting this low. So here we have 1 dB compression, and at this point it is known as P input 1 dB, and this is your P output 1 dB. So what do you mean by 1 dB compression point? 1 dB compression point are those points where your power output falls ideal value by 1 dB. Okay, are you getting it or not? Hello?
Yep.
Have you got this concept? 1 dB compression point where your P output falls to 1 dB. Are you getting it or not?
Yeah.
You need out.
No, it's okay.
Observe it. Okay. So basically in your slides, they given that your gain is 100, 1200 P in plus 306 P in square. Okay. Now they asked you to find 1 dB compression point. Find 1 dB compression point. Okay. Find 1 dB compression point when your P input is 100 or 20 dB. 100 is equal to 20 dB. So how you will find these 1 dB compression point? Are you getting it or not? You will take your gain will falls to, it means that what is your output? P output is P input by gain. So my output, the power gain, this is the power gain. So it will falls to 1 dB, to minus 1 dB, and that is equal to, what is your gain? 100 minus 200, and that is, and in place of P in you have to write P 1 dB, 1 dB plus 360 P 1 dB divided by 100, and you will get minus 1. So from here you will get the P 1 dB point, that is 0.018 or whatever you can say. Okay, are you getting it, this concept or not? So at this power, your output get, if you convert it into dB, it will be it. If you convert into dB, let me check dBm. It is log 0.018 into 10. It is minus 17.4. Yeah, around minus 17.44 dB. So your compression point is like that. You got at this power, this is 12.6 dBm. Your original, you wanted to have this much gain, but you are getting this much gain. So here 1 dB compression at this power. So this is known as 1 dB compression point. Are you getting it or not?
Yeah.
Are you getting it?
Yeah.
Okay. 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 After that, this was your 1 dB compression point. They have given you many slides there from where you can observe the graphs and all those things. Okay. Now, now we will see what happens if we will send 2 sine wave as an input in place of 1 sine wave. Till now, what we were doing, we were sending our input signal xt and getting yt, but here we are sending xt only one signal, only a cos omega t. Now what will happen if we send two signal together? Okay, then we have to see, that is two tone test, that is also known as two tone test. So what will happen, this is our v input. Okay, and this is a1 cos omega t plus a2 cos omega 2t. Okay, here we will get some output. Okay, so here we have to see what will happen to our output if we will send two input simultaneously. So our output will be have one DC term B naught. After that, we will have B1, A1, because first term will get square root. It will get square root. Another term, no, first term we will be normal. And we will have another term as a square root plus another term as a cube root. As cube root. So this I will get our output. But observe here, these are not our desired output. What we want, we have the two frequency component omega 1 and omega 2. Okay, but we will get different coefficient, and at omega 1 we are expecting the coefficient as a1 and a2. Okay, so our v output, if we will consider every other term, b1 by 3 4 b3 a1 square plus 3 2 b3 a2 square into a1 cos omega 1t Apart from that, we will have b1 plus 3 by 4 b3 a2 square plus 3 by 2 b3 a1 square, and we have a2 cos omega 2t. And apart from that, we have some other components also that I'm not writing, that is given in your figure, that are the another components also. So what happens, suppose this is your two tone, your input is omega 1 and omega 2, and you pass to it third order nonlinear system, you will get other components here. This is your omega 1, this is omega 2, and apart from that, you will get some small interference. Okay, you get small interference. This is known as intermodulation product. This is known as intermodulation product of your output. So we are getting two new components at new frequencies. Okay, that is one component is two. We are getting two new components. One component, let me write it only 3 by 4 b1 a1 2 a1 cos omega minus dot t plus 3 by 4 b3 a1 a2 a2 cos omega 2 plus dot t. So we are getting another two term that we are not expecting, that two term these are getting, and this is corresponding to those term. Okay, so these are the intermodulation product. The original tones are also scaled. Original tones are also scaled by and are also scaled. This was of our original term, and this was also got scaled. Okay, scaled and got shifted. Only odd terms of B and B are relevant. We wanted only odd terms to say here. Okay, so gain of one component is impacted by the magnitude of the other, and this is known as non-linear function, and this is also known as desensitization. Actually, what happens because of this we are sending, if we are sending two input, x1 and x2t, and we are getting yt, our output can get desensitized, and we can have cross modulation. Cross modulation in what? Suppose this is our original term and this is our interferer. So what happens due to cross modulation? This signal will get interfere with this signal, and this signal get interfere with this signal, and our original signal get distorted. Okay, so this is the disadvantage, and we have to check. This is not disadvantage. We are checking our system, that whether this system is how much can be desensitized and how much it can synthesized. So these we are wanted to check.
Mm-hmm.
If you have any doubt, then ask me. What desensitization means? That suppose this is your original signal, okay, and this is your interferer signal. But what happens, sometime your interferer signal is come in such a fashion so that your original signal get cancelled with each other, and your system will get desensitized. You will not get any output. That is known as desensitization of your system.
Okay.
If you have any doubt, then ask me in this one.
No.
Do you have anything to ask? Okay. And after that, we have IP3. Okay. IP3 is just like first order modulation. We have another modulation, another intermodulation product that comes in the picture when we have the different signal at the output. This also specifies non-linearity of system. Okay, if your IP3 is large, device is linear. Device is more linear. So ideally, we are checking our system whether its IP3 is more or less. If its IP3 is more, then it is more linear. If its IP2 is less, then it is not that much linear. So this feature or this characteristics of our system, we are measuring using IP3 and IIP3 and all these, and IIP3 and IP1 PI1 dB, even at 1 dB compression point. With the help of these things, we are measuring these things. So generally what happens, what is the idea behind this? In our linear device, our power output is directly proportional to input power. Okay, but it is not true in nonlinear. In nonlinear device, power output is not proportional to P input. Okay.
Mm-hmm.
So when we send our two sine waves, we are getting different interferers. you can see when we are sending two sine wave omega 1 and omega 2, we will getting omega 1, omega 2 and other two interferes. So now take that we are taking our P input. We given a P input as a P. What is the we have given V input as a cos omega t, right? So our P input will be power will be a square by 2r. Okay. Now from our previous explanation, we can get to know that when our B1 and A1 and A2 are equal, we can get to know that our P output will be this much, because in our nonlinear system we are neglecting odd harmonic get cancelled with each other. So we will get the P output as 1 by 2r B1, A1 and A2 are equal. A1 and A2 are equal. So we will get B1 by 9 by 4 B3 A square. So we will get B1 9 by 4 3 B3 A square into A to the power whole square. That we will get the P output that you can observe in slide 36. So power of the wanted signal at the output is not proportional to input. Here we can say that here our input is this, but here it is not proportional to the output. Okay. Power of wanted signal is not. If input is small, if suppose our input signal is small, A is small, then we can have the power output as B1 square P. Okay. If input is very small, and that we can tell it is a linear. But if input is not small, then we will get non-linear things, and that is not advantage for us. And that you will see, you will get output as a third term, as a three order. It means that you will get output. If you see the difference between when your input signal is small and when your input signal is high, your PD will be this much. That is 9 by 4 B3 square A cube P in cube. P in, not cube, P in. Okay, this is your third order line. So we will plot this line. And see how this looks like. So originally we were expecting that our curve will go in that fashion. But what happens? Due to unwanted signal, our curve follow this path, and this is known as your IP3. It means that at input power, when you are getting your output, third order of output get intercepted with the linear output, that point is known as third order IP3 point. Okay, and that other corresponding point is known as OIP3 at power output. That is known as OIP3. And what is OIP3? OIP3 is equal to gain into IIP3. Okay, are you getting it?
Yeah.
Okay, then you can see that in dual tone test, the IP3 point is a hypothetical point where the output power in a wanted tone equals to output power in an unwanted tone. That is your third order intercept point. We can write the IP3 point is hypothetical point where your MP3 where your output power in a wanted tone equals the output power in an unwanted tone. Okay. Okay. These your these are the your output, and there are there are the formulas for PIIP3 also. PIIP3 formula is 2 by 3R divided by B3 is your third order output. Okay. And what is your P output? P output is Z into PIP3. Okay.
Mhm.
Any doubt in these things? Then ask me. This is your
No.
third order intercept point. Similarly, they have derived your five IIP3 also, IIP5 also, and that is 1 by 2R 8 by 5 B1 B5. This is your 5 IIP3, and again IIP3, and also P output IIP5 equal to gain into PIIP5. Okay. Any doubt?
No.
If you have any doubt, then ask me, because we will, after that, we will start the oscillator and phase lock loop.
Okay.
Take a look on your slide once. Okay. Take a look on from slide number 36 to 54. Okay.
Mhm.
And tell me if you have any doubt.
Okay.
Slide number not 36, before that only. From slide number around 31 to 50 around, you can take a look. Tell me. Let me know once you get finished.
Okay. It's okay.
Okay, good.
Mhm.
Now see oscillators. Okay. Okay. Generally, what
Mhm.
happens? What first of all, the concept behind the oscillator is that we have the concept of PLL in before that. We have a two different type of oscillator. Okay, one oscillator that gives you fixed frequency. Okay, suppose this is your oscillator. Okay, and your it is giving you fixed frequency. Suppose you put an oscillator and your it is giving you a fixed output. Okay, that is your oscillator. Okay, but we have another oscillator also that are not giving you a fixed frequency, that are giving you a changes in the frequency depends upon your input. We have VCO, and depends upon voltages its frequency is getting changed, so that is voltage control oscillator. Okay, that is voltage control oscillator. Basically what it is doing, it is giving you fixed frequency f naught, and here we are getting a variable frequency, and these frequencies are getting changes depending upon the voltage. Okay, so that is known as VCO, voltage control oscillator. And in our wireless devices, this oscillator is very much used. Why it is very much used? Because our voltages are not constant at every point of time. Because of the noises, the voltages are getting changes every time. So we are getting different, we need to have the different frequency depends upon the voltages that being fed to the system. So that is the voltage control oscillator that changes frequencies depending upon the value of the control voltage input. Okay, that are being used in transmitter and receiver and all those things, that are the theory part. What is frequency established? Average frequency needs to be accurate and remain accurate as time. Yeah, its frequencies are accurate. Okay, and we have other parameter to measure it. Okay, so ideally what happened, let's see. Okay, frequency must be adjustable, that are the feature. Okay, now we will see to the general oscillator architecture. So generally what happens in our oscillator, we have positive feedback. So if some of the constructive frequency occurs, its loop gain is 1 and phase shift is 0. Condition of positive feedback. Condition is that if loop gain is 1, loop gain should be 1 and phase shift should be 2n pi. Okay, it can be 0 degree or modulus of 2 pi. Then we can say that oscillation can happen. Then we can say that oscillation can happen. Okay, so basically we have terms AJ omega BJ omega as gain, and that is equal to 1 plus J0. Okay, we could use LC circuit on the feedback path as one region. Okay, oscillator. Okay, there are different type of, this is the condition for oscillation. An oscillation can happen if it's satisfied following condition. It means that it should have positive feedback, loop gain should be 1 and phase shift should be 2n pi. After that, it can have the oscillation can happen. What do you mean by oscillation? Oscillation gives you a frequency, a free running frequency. Okay, just like sinusoidal frequency, you are getting a free running frequency. Okay, okay, and that with a fixed frequency. Okay, that above with fixed frequency. So now we will see LC oscillator. How does LC oscillator looks? LC oscillator, we have L and C component. We have L and C component, L component and C component. We could use LC circuit on the feedback path. These circuits are being used here in the feedback path. Okay, these circuit are being used here in the pad path. We could use okay, and this gain is, if you find the gain of this one, you will get J omega C minus 1 omega LC. Okay, and it has a resonant frequency F naught as a 1 by under root LC. Okay, and we can arrange that Barkausen criteria is satisfied at some frequency, but BJ omega has a low quality factor resulting. Okay, the thing is that the why the LC is that this is having low quality factor, low Q factor. Okay, and these are result in a low Q resonator, and its quality factor Q is less than 100. And also disadvantage is that BG omega is very much dependent on L and C values. Okay, these are very dependent on L and C values, so its stability is very poor. So we are going to need, so we need a better resonator or better oscillator. This oscillator is not good because its frequency depend upon L and C, and its stability is also poor. So this is the LC oscillator. Okay, and after that, the LC oscillator, we have quartz crystal oscillator. Quartz crystal oscillator or quartz crystal resonator. Quartz crystal resonator. The advantage of quartz crystal resonator is this is having good stability. Okay, because quartz is a piezoelectric material. It affects as a piezo material, and applied voltage causes the shape changes, or shape changes generate the voltage. What happens? Quartz is a piezoelectric. Quartz exhibits piezoelectric effect. Quartz exhibits a piezoelectric effect. Okay, so what does it do? Applied voltage cause a shape change, We apply voltage and shape gate change, and shape gate change, it generate voltage. Shape changes, shape changes generates the voltage. Okay, and it has a high quality factor, importance, high Q factor. Okay, these are having high Q factor, and this diagram is L, R, C, S, and CP. CP, CS, RS, L. Okay, we can have series resonance and parallel resonance also. Okay. After that, we have another precision control oscillator also. Here one it uses low phase noise. It is having a low phase noise, so it is a precise frequency stability is happening. Okay, we can choose this type of resonator also, depends upon our application. Okay, for this one, I can write that omega s equal to 1 by L CS and omega p equal to 1 by L C dash, where C dash is CP, CS, CPCS. Okay, this is the your quartz crystal resonator. Okay, no, and if omega p is very greater than omega s, if CP is greater than, if the value satisfy bifurcation criteria, then we can have a large quality factor. Okay, these are the oscillators. Okay, that's totally depends upon the fixed, these are giving a fixed values. Okay, now we can have a voltage control oscillator also. We can a voltage control oscillator that controls the voltages. So what happens, we use a LC oscillator and its resonance frequency and its electrical adjustment of resonance frequency, which in turn will vary the oscillation frequency. Okay, we have the VCO. So what happened, this is L, this is C. Okay, but what happens here, this C value depends upon, is controlled using a vector diode, using controlled by a vector diode. What does vector diode do? Vector diode changes the capacitance of the diode depends upon the voltage applied to it. Vector diode changes frequency, changes capacitance of diode depends upon the voltage applied. Okay, this is your vector diode, VCU. This is a voltage control oscillator, and that's why in voltage control oscillator we do not get a fixed frequency. We can get a frequency, different frequency depends upon the voltages that being applied. So that is the very good example, that is very good advantages of vector diode. Okay, so we will see how phase lock loop looks like. Phase lock loop is a very important circuits in a wireless system. It is used to to give a frequency. It is used to track the input frequency and phases, and we can get a stable output at the output of a system. See, phase log loop. Okay, how does phase log loop this? This is your phase detector. Okay, and this is your low pass filter. This is your VCU. This is your V input. This is your V output. So you can say when when we have the V input, we have a fixed frequency F in and phi m. Okay. Then when phase is logged, it means that it is tracking the phase. Then frequency of VCU is will be equal to input frequency. When phase is logged, when PLL is logged, then F input equal to FCU. Okay. And in this way it is tracking. So what happens now? Depending upon the input of our signal, we have the different frequency. Okay. The frequency, we are having the frequency, and according to that frequency, the phase is changing. Okay. These are changing the phase, and we are getting a output frequency. Okay. Depending upon this frequency, depending on these voltages, we are getting a output frequency using VCU. But what happens? Suppose we are getting this frequency, and this frequency will give you phase detector will give you null value when these frequency and these frequency are same. But when these voltage again changes, the frequency again change, then the V lock loop work. So what does it do? We first so for that we will first understand how phase detector will work. Okay, we will see that how we can consider that we have the two signal with same frequency. Okay, and with some phase shift. Suppose we have VCO with phase shift sine 2 pi ft plus phi VCO. Okay. Now think that this is your original frequency. Okay. Now observe. This is your original frequency, and this is your frequency with difference phase. Okay, with different phase. Now, what does do? A phase detector produced an output proportional to this frequency, this phase. So we have, suppose we have the different phases here. Okay, VCO and F input frequency are different phases. So phase detector will what will it do? It will check the difference in the frequency and convert that difference phases into output, VD, ET, error, into one output. Okay, phi in my phi VCO. Okay, and that is equal to KD delta phi. So what will happen if these are getting changes? If these are getting changes, so we are getting the different phases. So we are getting the different phases. So phase detector produce an output proportional to the phase difference. Okay, and KD greater than 0. So it will give a change in the voltage, and that change in voltage, VCU will detect that change in the voltage, and it will change the frequency, and frequency will change. And in this way, frequency will be same as the input frequency. So in this way, we are tracking the input frequency. Okay. Are you getting it? We have the digital phase detector. Then sometimes the input and feedback signal are digital, not sine wave. Then we are using